Hi there, everyone. Today we will learn about how a current, when it passes through the vicinity of a magnetic field, feels a force of that magnetic field. We learned in the past, just a little bit while ago, that if there is a charge, let's say we have a positive charge, and this positive charge is traveling to the right, and it encounters a magnetic field. Let's say the magnetic field is going through into the page. Then, using the right hand rule, that this charge will suffer from the magnetic field force because it's a traveling charge within the vicinity of a magnetic field. Now we can find out where that direction of the force is. We can apply the right hand rule. So this is my right here. This is the traveling. My thumb represents where the charge is going to the right, and the magnetic field is inside the vicinity of the page or the screen. Then the magnetic field force will be the palm of my hand up. So as soon as this charge goes into the vicinity of the magnetic field, it will be deflected like this up with a force, magnetic force, equal to FB. And this FB, we also found out that's equal to QV, the velocity, times the magnetic field, times the angle, sine the angle between the velocity direction and the magnetic field direction. Now, what happens if this charge is not free to move anywhere? And this, as an example of that, is a charge that is traveling inside a current, inside a wire. So let's say this is a wire, okay, and there is a current, which is a charge, delta Q over delta T, and this current is going in a certain direction. Then you expose this wire to a magnetic field. The same rules are going to apply because these are traveling charges and there's a magnetic field. Then the traveling charges will feel what? A force of the magnetic field. Perfect. So those charges, however, can't go anywhere because they are constrained by the wire itself, the physical boundary of the wire. So let's say those charges, I'm going to go here, they're going to try to go up, but the wire ends here. So they're going to hit this boundary, all right? And what happens then is that they are going to move the whole wire up. You're talking about millions and millions of charges being pushed in a certain direction into the wire. They are going, what they're going to do is just hit the boundary of the wire and they're going to push the wire up. So actually, the wire will feel the force, and the wire could bend a little bit sometimes if it was, not too thick of a wire, or if you can put this wire on an axis to rotate, then the whole thing is going to start rotating because of the force, and then you can make a fan, an appliance at home you can use. And that's how the idea came to engineers. All right. So let's look at this in more details here. So let's say we have a magnetic field. So I'm going to put a magnetic field. Here is the north of the magnetic field, and here is the south. So we know that the magnetic field direction is going this way. So that's the magnetic field direction. And let's say we have a wire, and this wire is coming from my side and going into the page. So this is the wire here. So basically the traveling V of the current is going down into the page, all right? Using the right hand rule, again, it's the same right hand rule for the traveling charge. We use this for the direction of the current. So the current is going into the page, okay? So I'm going to put that into the page. So to do that, look, this is the thumb where it shows where it's going inside the page, and the magnetic field direction is down. So the force would be what? To the left, this way, coming this way. So actually, this guy, which is a wire, is going to feel a force like this one. So as soon as the wire has a current going inside, the current will be pushed this way, and the current is constrained by the wire, so the whole wire will be pushed this way. Let's have another example. Let's say we have a magnetic field going this way, and we have a current that is going this way. So that's a current, I. Okay? All right. So we put our thumb like this for the direction of the current, and we put what? The magnetic field for this. So the direction of the current is this way and the magnetic field is this way. So for me, it seems that the current will be pushed downward. So the force, I'm going to put it this way, the force will be inward. So the current or the wire will be pushed down into the page, and so forth. So this happens all the time. That's how we actually transfer electric energy into mechanical energy. That's how your fan at home works. You put a current inside a loop of wires, and this loop of wires sits within the vicinity of a magnetic field. Once the current starts moving, the loop of wire starts feeling the force, and it turns around the fan. And that's how things work. Now, let's look at the value of this force. Now, we found out it exists. We found out its direction. Let's look into its value. Okay? All right. So, it was found out that this force here, so let's look at this current here. This magnetic field force on a wire carrying current is proportional to the length. So the longer the wire, the bigger the force. It was also found out that this force is also proportional to the current. Directly proportional to the current. The bigger the current, the bigger the force. And that makes sense. Okay? And of course, what do you think of the magnetic field? If we increase the magnetic field, what would be the force doing? Is it going to increase or decrease? I bet if you did this experiment and you will find out that it is directly proportional to the magnetic field. So basically what this tells us is that the force on a current or a wire carrying current will increase if the length of the wire increases, will increase if the current increases, will increase if the magnetic field increases. If we put all of these together, that's what the experiment tells us. If we put all of these together, we find out that the force on a wire carrying current will be equal to I, the current, L, the length of the wire that is exposed to the magnetic field, times the magnetic field, times there is an angle sine theta, just like we learned when the force acting on a traveling charge. For example, here, as you can see, there's the magnetic field and there's a current going this way. So there is an angle theta always. And this is, taken care of by adding sine theta to the equation. So this is the equation that we need to know very well. Maybe memorizing it or understanding it will also help a lot. So that's the force acting on a wire carrying current. I is the current inside the wire in amps or ampere. L is the length of the wire that is exposed to the magnetic field. B is the magnetic field, and theta is the angle between the direction of the current and the direction of the magnetic field. Okay? All right. Let's have a quick demo example to apply this. Okay, so look at this example here. We have a wire. In this wire, there's a current that is going this direction. Okay, and this wire has a length of 200 centimeters, and it exists within the vicinity of a magnetic field, and this magnetic field has 0.2 Tesla value. As you can see, the direction of the current and the direction of the magnetic field, between them, there's a confined angle of 40 degrees. All right. So now let's basically, we need to find the force acting on this wire. And knowing that I is equal to 3.1 amps. 3.1 amps. Okay. Okay. Let's use the equation from here. FB is equal to ILB sine theta. All right. So now FB, I want to do that. I is 3.1 times the length is 200 centimeters, which is 2 meters. Remember, we have to divide by 100 to get centimeters into meters. or to convert centimeters into meters. B is the magnetic field, which is 0.2. Now the angle is 40 degrees times sine 40. And if you do some calculation with your calculator, you can get the force is equal to 0.797 Newton, or almost 0.8 Newton. Now, 0.8 Newton is a small force, but look, a wire of 2 meters long exposed to that much of a magnetic field, this force will kick the wire out. It's too big. That's why they call it sometimes the kick experiment, because it's so sudden. And that's what engineers found out. Okay, hey, I can use this to make something. I can, I can make a fan. I can make a wheel turn. Okay, maybe if I put this wheel in a car, I can use the electric energy or electric cars and so forth. I mean, there is so many applications for this. All right, thank you.